Hello and welcome to this week 4 session on constraint and unconstrained optimizations. I'll wait for a few more minutes and we'll then get started with today's content. Okay, so it's already 3 p.m., but since no one has joined yet, I'll wait for a few more minutes and we'll then get started with today's content. So, yes. I don't know why this is appearing. Okay, now it's fine. Okay, so let me write it down. So today is something around 26. Okay. So the topics that I'll be covering today will include week 4 assignment discussion, then clearing one doubt which is there in the discussion forum, next will be to talk about the contents of this week 5 assignment that you will be having in few days time. I think that deadline is next Wednesday. So that will be a discussion on dual simplex method, then for this discussion on the Gomory's cutting plane method. Next will be a discussion on branch and bound method. Finally, problems similar to assignment 5. Okay, so let's get started with today's content. So first is this one, week 4 assignment discussion. I know the solutions have already been posted, but for the sake of like completeness, I'll just go through it. Okay, so let's start it. Yeah, so in week 4, the first problem was let xp star be an optimal basic feasible solution to the linear programming problem. Maximize z equals cx and subjected to the standard constraints that you have, and let us consider there is a reduction in the cost coefficient ck associated with a non-basic variable. So what happens is that suppose, let me write down the standard problem. Now subjected to what you have is that ck prime is ck minus delta ck, right? And xk doesn't belong to the basis, or you can call it as xb, right? Then what happens is that you can calculate zj minus cj, which is the reduced cost, and this remains as, so this will be greater than equals 0, or for basic variables it becomes, if I'm not wrong, it becomes 0, right? So the reduced cost is 0 for basic variables. For all j belongs to the basis, or rather let's say index of that basis. And for others, what happens is that, so earlier you had this, right? So this zk minus ck was greater than equals to 0 for non-basic variables. Now what happens? Your changed solution, now it has ck minus delta ck, right? So this becomes zk minus ck plus of delta ck. This is the new reduced cost. That means what happens is that this part is already greater than equals 0, and this is something which is greater than 0. So this becomes greater than 0 for all non-basic variables as well. So optimality do not change. So therefore the answer will be optimality of xp star will not be affected. Will not be affected. Right. Okay, so option B is the correct one. Okay, so let's move on to the second problem. So here what you have is that let xp star be an optimal basic feasible solution to the linear programming problem. So it is given as it is, and it is given as beta ik is the ith element of the optimal basis or B inverse. So there is a change in the requirement vector B such that, so what happens here is that, so this changes to this. Now you can calculate the current optimal solution needs to have the feasibility criteria, and I think this has already been discussed. in the class. So I'm not going into the proof of it. So it's beta ik greater than 0 minus xbi divided by beta ik. So this has to be less than equals to delta bk less than equals min of beta ik less than 0, and this should be minus xbi divided by beta ik, right? So your answer would be A. Now let's get into the third problem. So the third problem says which of the following statements is true about the dual LPP. So it says any feasible solution to the dual provides a bound on the objective of the original primal problem. So option C is the correct one. So that had been already shown in the class, I think. So any feasible solution to the dual LPP provides a bound on the objective of the original primal problem. So by some, I think strong duality and weak duality, those things are not covered in this course probably. So what happens is that suppose your primal is a maximization problem. So you can start from here and you try to maximize it, right? And probably your optimal should be somewhere here. And so this is your primal feasible region. And your dual feasible region could be, so that could be a minimization problem. So you're trying here, 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 and you're moving in this direction. So this could be a dual feasible region. And this would be this primal and dual optimality. So I'm talking about the objective function. So they should match. So what happens is that any feasible solution to this dual LPP, so you are in this region, so that will provide an upper bound to the objective of the primal solution. So that's the idea. So I think you have understood this. Let's move to the fourth problem. So this should says that which of the following statements is or are true. So there are actually two answers which is correct here. If any variable of the primal problem is unrestricted in sign, then the corresponding constraint of the dual is an equality, so that's true. Another, if any constraint of the primal problem is an equality, then the corresponding variable of the dual is unrestricted in sign. So I think I showed you in the previous class as well how to like prove this as well. So the answer is A is if any variable of the primal problem is unrestricted in sign, then the corresponding constraint of the dual constraint of the dual is an equality. And C tells you if any constraint of the primal problem is an equality, then the corresponding variable of the dual is unrestricted inside. Okay, so that's fine. Let's move on to the fifth problem. So given an LPP, you have to formulate the dual of the LPP. So the problem is given as max of, just a minute. I'm recording this. Okay. Yeah, so max of z equals 2x1 plus 3x2 plus 4x3 subjected to x1 minus 5x2 plus 3x3 equals 7. And then what you have is 2x1 minus 5x2 less than equals 3 and 3x2 minus x3 greater than equals 5. And you have x1, x2 greater than equals 0. x3 is unrestricted in sign. So this is your primal problem. Next, let's go into the dual problem. So let's call it as v1, the variable associated with this dual. So this is v3, and how we can write it. So this will be a min problem, and let's say w equals 7 v1 plus 3 v2 plus 5 v3. What you have to do additionally is that yeah, hopefully my screen is visible. I think it froze. Just a minute. Because of the internet connectivity, I think. Okay. Yeah, now it has appeared. Yeah, so this is 7v1 plus 3v2 plus 5v3. Sorry about the quality. I think today internet is not working well here. But anyway, yeah. But while you do that, there is one issue here. So what you have to do first, you have to change it to standard form. So this equation, you can write it as x1 minus 5x2 plus 3x3 less than equals 7, and another one you can write it as minus x1 plus 5x2 minus 3x3 less than equals minus 7, right? Yeah, and this one you have to convert it into less than equals to type, so that means this becomes minus 3x2 plus x3 less than equals 5, minus 5, right? So that means the right hand side of this changes to minus 5, so that's why this should not be a plus 5 v3, so this should be minus 5 v3, so you have to be careful about that. Next, what you have to do, what you can do subject it to, you can write down the constraints. So corresponding to V. The first one, what you can write is V1, and the next one is plus 2V2, and the third one doesn't have any term related to x1, and x1 is greater than equals to type, so this should be less than equals to this sorry, not less than equals to. So in dual it becomes greater than equals to, so this becomes greater than equals to 2. Next one is minus 5v1 minus 5v2. The next one you have converted it to negative sign, so that becomes minus 3v3, and since x2 is also greater than equals to 0, so this becomes greater than equals to 3. That's fine. And the last one, that becomes 3v1 then plus v3, and since x3 is unrestricted in sign, so this becomes equality sign, and finally you have 4. And now based on the types of v1 will be unrestricted because the first constraint was of equality type, and v2 and v3 are greater than or 0. So that's about it. So answer will be option D. Yeah, next one is construct the dual of the LPP and solve both the primal and dual. So I'm not going into solving it because you can do it in Excel, but probably it will be a good time to show it in Excel today. So let's do that actually. So first let's write it down. So max of z equals 3x1 plus 4x2. Okay. So it's appearing again. Okay, so I think my internet is not working well, so let me try and reconnect it. Okay. I've switched to another network. Yeah, hope I'm still in the call. Yeah, now it's working. But yeah, the quality is not up to the mark, but anyway. So this subjected to what you have is x1 plus x2 less than equals 12. Then what you have is 2x1 plus 3x2 less than equals 21. Finally, what you have is x1 less than equals 8. And you have also x2 less than equals 6. And finally, it's x1, x2 greater than equals 6. Now you have to solve this, but also you have to convert it into dual. Right? So this is your primal. And let's construct your dual. So let's have it as v1, v2, v3, v4. Yeah, everything is of less than equals type, so that's not a problem. So the dual will be a min problem with 12 v1 plus 21 v2 plus 8 v3 plus 6 v4 subjected to it's v1 plus 2 v2 plus v3 plus v4 greater than equals 3, and another one will be v1 plus 3. Okay, I think that there should not be any v4 here because x1 doesn't appear in that equation. And this one will be 3v2 plus v4 greater than equals 4. and all of them were of less than equals type constraints. So v1, v2, v3, v4 or else greater than equals 0, right? So let's solve this problem. So now I know you can solve it by simplex method, but it is time consuming to do that right now. And you already know the techniques of solving it by simplex method. So let me show you in Excel and how you can get this solution very easily. And then I think you can just have it for a verification purposes. So let me unshare this screen and join with Excel. Okay, so let me open Excel. Okay, so it's opening the other device. All right, so let me share that screen. Yeah, so I think it's visible, and let's do it. Yeah, so let's solve it in Excel actually. So let me write down the primal form first. So this is your primal problem. Max of 3x1 plus 4x2, right? 3x1 plus 4x2. This is subjected to, let's write down the constraint, x1 plus, sorry, plus x2 less than equals 12. Next one is 2x1 plus 3x2 less than equals 21. Then as x1 less than equals 8, x2 less than equals 6. Oh, sorry, it was 6. Right. And x1, x2 are greater than equals 0. So this is your primal. Let me save it first. Yeah, so the next part is dual. So the dual problem is a min problem, and it's 12v1 plus 21v2 plus 8v3 plus 6v4. Okay, so this is your objective, and this is subjected to two constraints. First one is v1 plus 2v2 plus v3 greater than equals 3. Next one is v1 plus 3 v2 plus v4 greater than equals 4. Then you have this standard one, v4 all are greater than equals 3. Okay, so this is your problem. So these are your data actually. This is your primal problem. And and this is your dual problem. Now what you have to do, you have to solve problems, right? So first what you will write it as the objective function. So for this problem, so let me write down here, okay, let me write down here itself. The objective is okay, so let's first write down the variables. So x1 and x2 are the two variables here. Let them initialize to 0. Your objective now will be a formula which is 3 times x1 plus 4 times x2. So this is your objective. Let's write out the constraints. So constraint. So let's call it as Z, and let's call the constraints as G1, G2, and so on. So this will be x1 plus x2. The left hand side I'm writing first. That's here. And then the sense is less than equals, and the right hand side is 12. So this is fine. G2 is 2 times x1. Oh, so sorry. So this is 2 times x1 plus 3 times x2. This is your LHS, and your LHS is less than equals 21, right? Then you have G3. So this is nothing but just x1, right? And this is less than equals 8. Finally, G4 is nothing but x2, and this has to be less than equals 6. And the non-negativity constraint, we don't write it down explicitly, we can provide it later. Anyway, so let's insert, yeah, just a gap. Now for the dual problem, what you have is you can again write down the variables and the constraints. So let me do one thing. Let me write down the variables from here. So this is v1, v2, v3, v4. This is your objective W. Then probably your constraint, let's call it as G5 and G6. And let's call it H1 or H2. Let's write down these expressions now. It's 12 times, not this one. First you have to initialize them to zeros. Here, let's write down. It's 12 times v1 plus 21 times V2 plus 8 times V3 plus 6 times V4. So that's the initialization. Next, we'll write down the constraint. So that's V1 plus 2 V2 plus V3 and this should be greater than equals 3. And finally, you have to write down the second constraint, which is V1 plus 3 V2 plus V4. This has to be greater than equals 4. So now you have given all the data and you have to solve this problem. So how to solve this? So let's do that. So as I've shown you before, you can go to data and you can go to solver. Yeah, it's opening. Yeah, so the solver parameter, so you have to provide. So objective, this is first solve, let's solve the primal one. And the objective is nothing but this one, D12, and this is a maximization problem. Changing the variable values, I think this x1 and x2. Okay. Now you have to add the constraints. First constraint is some issue with my laptop. Okay, let's add now. So this is add. Second is this one. And the right hand side is this. Add. Third is this one. Right hand side is this. Add. Fourth is this. Right hand side is this. Click OK. Yeah, so you have added 4 constraints. Now you have to select simplex LP. So the method by which you're solving is simplex. So these were how you have provided the input data and the steps followed in the simplex method. That's not being shown here because the solver will take care of it. And yeah, this is your objective. So everything is set. And you have to make unconstrained variables non-negative. So x1 and x2 are non-negative. So this must be checked. And now you can have a solve. Sorry about that. Yeah. Okay, so I can have a sensitivity report as well and keep solver solution, and I can click OK. So this will add a sensitivity report as well. So reduced cost you can get from here. So it tells you the ZJ minus CJ values. Sorry. And all the reduced cost are 0. So you have 2 variables here. So that's fine. And you can also get some shadow prices from here and some sensitivity analysis. But yeah, I'm not going into the details. So the objective function is 30.67, which is 92 by 3. That was there in one of the options. And x1 is 8, so that's fine. And x2 is nothing but 1.67, which is 5 by 3. So yeah, so this part is fine. Let's solve the other part as well. So let's open solver again. Yeah, so let's change everything here. Now minimize, you're minimizing W. By changing the cells, this delete. So this is the 4 cells you have to pick. Here it's let's delete everything. Yeah, let's add it. So you can select these two together, and you can put a greater than equals here, and you can select this two together. That's you can select OK. So those two are here. Simplex LP make unconstrained as like that and solve. So you can solve it. Objective must be a formula. Okay, so let's see which one I picked. So I have to pick J12 here. Sorry. I think others are fine. Yeah, so you can sensitivity. Okay, keep solver solution and okay. So we got two sensitivity reports. But yeah. So now you can notice your Z and W both are same. So the primal and dual solutions are same 30.67. That is your Z max or W min, whatever you call it. And here you can get the V1, V2, V3, V4 value. So this is 0. V2 is 4 by 3, so that's fine. V3 is 1 by 3 and V4 is 0. So yeah, so that matches our answer. So that will be like the solution, which is correct answer is D. So let me stop sharing and go back to my tab and write. So I'll share this one later anyway. So let's do that. Okay, so I have already shown you the method to solve that problem. So the answer is, let's write down the solution. So that's obtained from the Excel sheet. Okay, so the solution is V1 equals 0, V2 equals 4 by 3, V3 equals 1 by 3, V4 is 0, X1 is 8, X2 is 5 by 3, and what you have is Z max is 92 by 3. So your answer is 80. So this is the answer. So that's 6. Problem 6 is fine. So let's move on to the problem 7. So construct a dual of the LP and solve both primal and dual. So let's again do the same kind of exercise. So this is subjected to x1 minus x2 less than equals 1, x1 plus x2 greater than equals 4, and x1 minus 3x2 less than equals 3, x1, x2 greater than equals 0. So let's solve this. So this is your max problem. So for min problem, first let's convert this. This is your primal. Let's write your dual. Your dual is a min problem, and let's call this variables as before v1, v2, v3. So this is nothing but min of v1 minus 4v2 plus 3v3 is subjected to constraints will be v1 plus, sorry, this should be minus v2 plus v3. So that should be greater than equals 3. And the other one will be minus v1 minus v2 minus v3 v3 should be greater than equals 4. And since all of them are less than equals type constraints, so this v1, v2, and v3 are greater than equals 0, right? So let me solve this problem again in Excel, and I think then you'll be able to understand what's going on. Okay, so let's solve this. Yeah, as before, I'll just unshare and share this part. Yeah, I'm doing it like this because it's easier to do in Excel, because I don't want to do this hand calculations today. So let's do one thing. I can create another sheet. So let's call it sheet 4, and let's copy everything that's there in sheet 1. And bring it to sheet 4. Okay, so the formulas and everything is copied. Let's zoom in. Okay, so now the constraints have changed. So for this problem, this is x1 minus x2 less than equals 1. For the next constraint is x1 plus x2 greater than equals 4. And for the next one is x1 minus 3x3. So I'm editing here itself because it's easier to do. And it's less than equals 3. But you don't have anything like this. And x1 and x2 are greater than, oh sorry, so it should be, okay. I have to redo it anyway. Yeah, so this is your primal problem. Now your dual problem is min of this whole thing needs to be changed. v1 minus 4 v2 plus 3 v3. And this will be v1 minus v2. v1 minus v2 plus v3 greater than equals 3. It's fine. Minus v1 minus v1 minus v2. Okay, so actually let's write it down the other way because it's difficult. So it's v1 plus v2 plus 3v3. That will be less than equals minus 4. And here you have only three variables. So this is your problems, primal and dual. So let's construct this. Let me initialize x1 and x2 to 0 as before. And I have to, this formula is correct, 3x1 plus 4x2, so that's fine. Yeah, this formula I have to change. So this is this minus this. This next equation, it will be x1 plus x2. For the third equation is x1 minus 3x2. You don't have any g4 here, so let's delete it. And you have to change this one. And the right hand sides are 1, 4, sorry, it's 1, 4, 3. So that's all about your primal problem construction. For the next one, let's delete v4 first. And you can bring these things up here. Okay, anyway, so I'll change that. This is 0, this is 0. Yeah, so let's write down this. Or I think it's better to keep it aligned. Okay, so let's do one thing. Then let's write down this formula again. So it's J8, which is V1 minus V2 plus V3. So that's fine. Oh, okay, so that should be objective. So that's V1 4 times V2 plus 3 times V3, right? So this is fine. Next one is the first equation, so that's V1 minus V2 plus V3, so that's fine. And the next one is V1 plus V2 plus 3V3. Okay, so let's change the signs. So this is fine. This is greater than equals, but this is less than equals. This is 3 and this is minus 4. Okay, so I think I have constructed the problem again. Now it's time to solve it, right? So let's solve it as before, data solver. And let's first solve the primal problem. So the primal problem objective is this one, D12. This is a maximization problem by changing the variable values here. Now you have to add the constraints. So this is less than equals and this is 1, so that's add. This is greater than equals, so let's add. Finally this less than equals and this is 3. Okay. So let's select simplex and non-negativity. So let's solve it. Yeah, so that's the message you get. The objective cell values do not converge. And there is kind of, so solver can make the objective cell as large or small when minimizing as it wants. So that means for a maximization problem, the solution can be as large as possible. So there is one option, I think, the primal has an unbounded solution. So the option C is correct because that's the message that you are getting from the solver. And you can also get it like while doing that mean ratio test while solving it by simplex method. That everything is negative and you can make it as large as possible, right? So that's one thing. And then the dual solution, let's try to do it and see what happens. Uh, yeah, so for the dual, let's solve it again. Yeah, so it gives one random value, but it's not like that. You can like make it as large as possible, right? So it gives you one solution which is 2.5 and 1.5, but it turns out that uh, even if you kind of make it uh, probably okay, hmm, so we can probably make x1 very large and also x2 very large as well, and then also you can satisfy those constraints. Okay, so let's move on and solve the dual. So here the objective is this cell J12, so that's fine. This is a min problem, and the variable values that you are changing as this 3, and let's delete this constraints first. Now let's add them one by one. So this is add, then this is minus 4, right? Okay. So this is as before, and let's solve it. Yeah, so here it says solver could not find a feasible solution. Solver cannot find a point for which all constraints are satisfied. So that's the difference that you need to notice. And option A says the dual has no feasible solution. So that's the correct answer. So that means you have two solutions. That one is the dual has no feasible solution and the primal has an unbounded solution. Okay, so I'll move on to problem 8 and I'll directly solve it in Excel because it says use duality to obtain an optimal solution if any to the LPP. So yeah, you can solve it by duality theory or the dual simplex method, whatever you call it. But let's solve it in Excel first and then probably I'll go back and solve it using duality. Okay. So let me just quickly make a note of the previous problem answer and then able to see later. So answer was A, which is the dual has no feasible solution that you have already you have checked from Excel, and C, the primal has an unbounded solution. Okay, so let's move on to the next problem, which is problem 8. So problem 8, let me write it down in my tab first and it will be easier for me. So just a minute, hold on. So it's max of 5x1 minus 2x2 plus 3x3. This is subjected to 2x1 minus 2x2 plus x3 greater than equals 2. Then you have 3x1 minus 4x2 less than equals 3. And you have x2 plus 3x3 less than equals 5. And you have x1, x2, x3 greater than equals 0. So let's solve it. So let's solve it by Excel first. Okay, so then I'll probably talk about the other methods. Okay, so let me open another sheet. Okay, so the problem is now, yeah, is the screen visible? Okay, yeah, it's visible. So it's 5x1 minus 2x2 plus 3x3. This is subjected to, so it's 2x1 minus 2x2 plus x3. This is greater than equals 2. Next one is 3x1 minus 4x2 less than equals 3. Then it's x1, sorry, it's x2 plus 3x3 less than equals 5. And x1, x2, x3's all are non-negative. Okay, so let's solve it. So first, as before, I'll write down the objective. So, but first it's the variable. So this is x1, x2, z, g1, g2, g3. Okay, set this to zeros at first. So it's 5 times. Oh, you have another, right? So it's 3. So it's x3, z. Okay, so now you can write down 5x1 minus 2x2 plus 3x3. Next one is 2x1 minus 2x2 plus x3. Then it's 3x1 minus 4x2. That's fine. And the last one is x2 plus 3. Oh, what did I do? x3. That's fine. Now this is of greater than equals, this is less than equals, this is greater than equals, and this is 2, 3, 5. So as before, let's solve it. So this is my objective, maximization problem, and changing the cells. Now you can add the constraints one by one. So this is greater than equals 2. So you can add that. Next is this is less than equals 3. Finally, this is greater than equals 5. Okay, so your constraints are added. Make unconstrained variables as non-negative, simplex LP, and solve it. Okay, so it gives you it doesn't converge, but it should not happen. Probably I have made a mistake. Okay, but I think the message is it doesn't converge, and probably you can make it as large as possible. Okay, so let me check. Actually, this problem, I think it's better to solve it because what's happening is that mm, okay, I think I made a mistake. This should be less than equals to type. And now let's solve the problem. So the last one you need to change it. So this should be less than equals to. Yeah, now let's solve it. Yeah, now it has converged, and let's get the sensitivity report. Yeah, the solution is now x1, which is 7.67, which is 23 by 3. So that's option C, right? So x2 is 5 and x3 is 0. And your Z max is 28.33, which is 85 by 3. So your option C is the correct answer. So yeah, so you can get it like this as well. So let me write down the solution. X1 is 23 by 3, X2 is 5, X3 is 0, and Z max is 85 by 3. Okay, so let's see if I can solve it by other method. Okay, so actually let's not get into, so you can, what you can do, you can create a dual problem of it and you can directly solve that using simplex method and you will get the solution. But yeah, simplex method, since it's not the topic of discussion in this week's content, I'm not going into solving it because it's the same boring thing of doing those calculations, right? So let's not get into that. Okay, so let's solve. Let's talk about problem or questions 9 and 10, and probably I'll then go into the next topics. Okay. So again, let's share unshare this. Okay. So as I've written down, this seventh question has two answers. The dual has no feasible solution, and the primal has an unbounded solution. And problem 8, as I have shown you just now, it's is it appearing a little? Yeah, there is some lag. Yeah, yeah. X1 is 23 by 3, X2 is 5, X3 is 0, and Z max is 85 by 3. Okay, so let's solve the rest of the two problems and then let's get into the methods. Okay, so the ninth problem says that which of the following is or true about dual simplex method. So first one is the initial simplex table should produce an optimal and infeasible solution. So that's true. Initial simplex table should produce a feasible solution. That's not true. Initial simplex table should produce a non-optimal and infeasible solution. So that's not true. So yeah. So the problem 9 is self-explanatory and it says that the initial simplex table should produce an optimal and infeasible solution. And problem 10 is which of the following is or not true about the dual simplex table. So the first one says the variable which enters the basis is identified before the departing variable which enters the basis. No, that's not true. And the other is the variable which departs the basis is identified before the entering variable. Yeah, so that's true because uh, yeah, first you check for that feasibilities and so on, right? Because optimality is always satisfied. So dual simplex table, the variable which departs the basis is identified before the entering variable. Right? So that's all about week 4 assignment, right? So yeah, I think you'll be able to. Yeah, I think you were able to solve this, and it is not that difficult. And let's now move on to the next thing that I wanted to discuss. So let's talk about it. So yeah, clearing the doubt and discussion forum. Yeah, after that I'll go into today's content. Yeah, so in discussion forum, someone asked, so let me just quickly check. Yeah, so please explain how to get the fractional part of for first slack variable in garments problem in lecture 23 because I did not understand how to take fractional part in Gomory slack variable. Okay, so fractional part in Gomory slack variable, right? Okay, so let's write down. So suppose I write x equals x int plus x fraction. So example, say 5.5 equals 5 plus 0.5. So this is the fractional part here. Suppose 1.2 is nothing but 1 plus 0.2. So this is the fractional part here. When I give it to as 4, so that's 4 plus 0. So that's the fractional part. Now suppose I give you minus 3. So that's fine. Minus 3 plus 0. So this is the fractional part. But let's say I give you minus 3.4. So what's the fractional part? So here, if you put minus 3 plus something, then this part becomes negative, right? So that's not allowed. So what you have to do here is that it's minus 4 plus 0.6. So the fractional part, instead of writing it as minus 0.4, you write it as plus 0.6. So this is the correct one. Now, how to get it for any x? So now, x fractional is nothing but x minus x int, where x fractional is greater than equals 0 that I have mentioned. The one way of getting it is x fractional is nothing but x minus floor of x. So now example, say x equals 5.2. So x fractional is 5.2 minus floor of 5.2, which is 5. So it's 5.2 minus 5, which is 0.2. Now, second one, say x equals minus 2.7. Then what happens is that x fractional is minus 2.7 minus floor of minus 2.7. So the floor of minus 2.7 is minus 3. So that's minus of minus 3. So you will get back 0.3. Yeah, so that's how you get the fractional part, right? Yeah, in the garments problem, I don't recall exactly what was the value of this x variable, but anyway, this is the technique in which you get it. Yeah, so that's pretty simple. Yeah, so I'll just quickly reply to that and probably I'll just then continue with the discussion of this week. Okay, so let's quickly fractional part for the Gomories. Yeah, so I think it should be fine. Yeah, it's x minus floor of x. Yeah. Okay, so let's post this message and then get. Yeah, so let's move on to a discussion of the next topic. Yeah, I've explained this in this video, so that's thing should be understandable. Yeah, so next was what I wanted to discuss is I think Gomory's cutting plane method and then our dual simplex method, I think, and then Gomory's cutting plane, branch and bound, and assignment 5 problems probably. Okay, so let's see how much time I have. Uh, yeah, so dual simplex method, I think you'll find in assignment 5, right? Let's see what's there in assignment 5 and discuss this together. Okay, in just a minute, I'll get the assignment 5 thing ready. Okay, so I think I downloaded it. Yeah, so the first problem is similar flavor. So assignment 5 problems 1. Okay, yeah, someone has joined, I think. Oh, and then left again, I guess. Anyway, yeah, problem 2 is similar. Yeah, problem 2 is similar. 3 is yeah, 3 is on dual simplex as well. 4 is on dual simplex. 5 is on dual simplex as well. Yeah, so next is Gomory's method. Yeah, so you have 6, 7 using Gomory's method. Branch and bound. Problem 8 is on branch and bound. And problem 9 and 10 is also you can solve it via branch and bound, right? Okay, so let's do it one by one. So first is this dual simplex method. Let me solve a similar problem. Mm, yeah, so in for simplicity, let's take two variables. Yeah, so let's minimize 5x1 plus 3x2 subjected to 6x1 plus 2x2 greater than equals 6. 4x1, oh sorry, 4x1 plus 3x2 greater than equals 6. And another one is x1 plus 2x2 greater than equals 3. And x1 and x2 are greater than equals 0. So let's solve this using the dual simplex method. Yeah, so let's convert it into standard form first. So what you have is you can move it max of z equals minus 5x1 minus 3x2 subjected to 6x1, or I think it should be minus 6x1 minus 2x2, and then plus x3 equals minus 6. Then it's minus 4x1 minus 3x2 plus x4 equals minus 6. And it's minus x1 minus 2x2 plus x5 equals minus 3. So this should be again plus 0x3 plus 0x4 plus 0x5, and this should be x1, x2 until x5, all are non-negative. So as you know, in dual simplex method, you don't care about feasibility to begin with, and you have to maintain optimality at every step. So let's do it this way. So let me write down CB XB B should be X1, X2, X3, X4, X5, and here you can write CJ. So this is nothing but minus 5, minus 3, 0, 0, 0. Okay. And what you have here is that CB is so to begin with, x3, x4, and x5 will be the basis. So then write it as a3, a4, a5. Here you can write it as 0, 0, 0. You can write this as minus 6, minus 6, minus 3. And you can just fill the rest of the table. Okay, so let's calculate. So this is 5. So you're maintaining optimality because every one of them are greater than equals to 0. Now, what you can do, you can take min of say this minus 6, minus 6, and minus 3. So this is minus 6. And right now I'm not going into the tie breaking, but what you can do, you can take x4, say as the departing variable. In that case, what happens is that, so say x4 is departing. Now calculate max of uh, 5 divided by -4, comma 3 divided by -3, right? That's -1. So this one is max. So that means x2 is entering. Now what you can get from here is that this will be your pivot, right? So you have to divide this by -3. Yeah, I think it's easier to do it in Excel. Uh, yeah, the calculations will become easier, but let me finish it off here. So now x3, x2, x5, and what you have here is that okay, and yeah, the first one, what I will do, I will just divide it by -3, so that becomes 2, 4 by 3, 1, 0, -1 by 3, 0, right? And for the next one, you have to make it as 0. So what you can do, you can just subtract directly. Please check. No, you have to multiply it by 2 by 3 and subtract. So R1 prime is nothing but R1 minus 2 by 3 of R2. And your R3 prime is nothing but R3 minus 2 by 3 of R2. Sorry. Okay, so I'll do undo. Yeah, so that's fine. Now let's make this calculations in Excel. I think that will be easier for me. So I'll just do the calculation in Excel and write it down. So let me write down the tableau. It's -6, -6, -2, 1, 0, 0. Next one is -6, -4, -3, 0, 1, 0. Then you have -3, -1, -2, 0, 0, 1. And yeah, I can write it as x3, x4, x5. Okay. So I'm just writing it down. Yeah, I'll share the sheet later so you can have a look from there as well. But yeah, calculations becomes a lot easier if you do it in Excel. Okay, so let me write down quickly. So 53000. Yeah, so let's drag everything. So it's the first one you are dividing it by -3. Yes, I've written it correctly. Next one is nothing but uh, whatever you had minus 2 by 3. Okay. The last one is whatever you had minus 2 by 3. Okay, so I think I have made it correctly. Yeah, and this formula needs to be written right. CB is -3. Anyway, what it means is, yeah, so I'm doing it currently. Plus, okay, so it should be times this times this plus this minus this. Oh, okay. I made a mistake. Hmm. Okay, so this should be. Okay. Yeah, so what happens is that in the next step, you will get something like, let me write it down directly, minus, this will be minus 10 by 3, 0, 1, uh, minus 2 by 3, 0, and the next one will be 1, uh, this is 5 by 3, this is 0, 0, minus 2 by 3, 1, and this is nothing but 10010. So this optimality criteria is satisfied. But again, you will notice that this x3 is departing. because that's negative, right? And again, you have to calculate uh, max of 1 divided by minus 10 by 3, and then what you have is this one, 1 divided by minus 2 by 3. So that will give you minus 3 by 10 is the, so x1 will enter. Okay, so automatically this becomes your pivot. And let me write down the another step of this problem. So what you will get from here is that this is x1, this is x2, this is x5, this is a1, a2, a5, and what you have from here is that you have uh, it's minus 5 and minus 3, right? 0. And now the first one, so r1 prime will be r1 divided by minus 10 by 3. R2 prime will be R2 minus, uh, rather it should be 3 by 4, like 4 by 10. That's 4 by 10 times R1. That's 4 by 3. Yeah. And R3 prime is nothing but R3 minus, okay, so that will be, or rather it should be again plus 5 by 10 if I'm not mistaken. Okay. Yeah. So let's quickly do that again and write down the values. Okay, so I'm doing it in Excel that I will share with you. Okay, so now it's minus 5, A2, sorry, it's A1. The previous step it was A2. That's A2. So this is X1, X2, X5. Now, what you have to do, this one, the first row, you have to divide it by minus 10 by 3. Okay, and the next one, what you have to do is whatever you had, D13, okay, plus 4 by 10, okay, plus 4 by 10, and the final one is just a minute. Yeah, whatever you had plus 5 by 10 times that row. Okay, give me a minute. Okay, so that's great that I already got something. Okay, so now I'm getting 0.610 minus 0.3, 0.20. From here I'm getting 1.2011. Yeah. Next is x4, which is minus okay, 1.201, 0.4, 0.6, okay, minus 0.60. This is 0, 0, 0, 0.5, minus 1, 1. So that's fine. Finally, what you have is this is 0, 0, 0.3, 0.8, and finally 0. Yeah, so from here, what you can notice is that uh, ultimately all of these are positives. Optimality is satisfied and feasibility is also satisfied. So your x1 star is 0.6, x2 star is 1.2. So let's plug it back to the original equations and see. So 0.6 and 1.2, right? So in that case, what happens is that 3.6 plus 2.4. So the first equation is satisfied. Second one is 2.4 plus 3.6. So second one is satisfied. Third equation is also satisfied. And yeah, so yes, that was 5x1 plus 3x2. Yeah. So z star 5x1 plus 3x2 says I think 3 plus 3.6. So that will be 6.6. So this is the correct answer. Yeah, so you'll find probably some similar problems in assignment uh, 5. So that's on dual simplex method. So yeah, I'm not say going into more details of dual simplex method because that's discussed, and I think you can answer the first 5 problems quite easily. So the first problem is similar, solve it using dual simplex. Second is that. Third one is something which you have to think about, and I think you have already done it in the probably seen it in the class, so that's fine. Fourth one is again, yeah, you have to do some sort of an basic things that you need to know about dual syntax. 5 is fine. Sixth problem is on Gomory's method, and yeah, yeah. So that one thing that can be done, Gomory's method, and then yeah. So what I'll do today, so I'll just have some 10 minutes remaining. So I'll just probably briefly talk about this Gomory's method and branch and bound method, maybe just the ideas of it. Probably will solve some problems related to this in the next class, and I'll be discussing assignment 5 solutions. Okay. So let's start with Gomory's cutting plane method. So now, so this is for integer programming. So in case of linear programming, what happens is that, suppose, as we have seen by graphical method, probably this is one of your constraint, this is another constraint, and probably you have this x-axis as your constraint. So this entire thing, so this is feasible region for LP. But for integer programming, which is IP, what happens is that probably you have this constraints defined, but after that, what you have is that these are integer variables that it can take. So x1 and x2 are two variables. So it might happen that, so these points that I'm drawing, these are integer points, right? Okay, so let me show it. So I don't know why it's happening like that. Some issues with my stylus. Yeah, so these are your integer feasible points. And that's your feasibility region now. So all the points in between are not feasible, but what you will do is that uh, there is one concept called convex hull. I think that's not being taught here in this course, but it's good to know. So if you can take a rubber band and kind of stretch it, and if these points are exactly covered by that, so that's the smallest possible area of the rubber band that you can have that can contain all these points. So probably this. So if you can reach up, so if somehow you can get to this part and if solve this problem as LP with this kind of constraints, then the solution of your LP will be same as the solution of your IP, right? So that's the idea because the corner points now will become feasible in this case. And again, you can evaluate those corner points and you will get the solution. And that corner point is integer point here. So, but how to get to this convex hull? It's one thing is what is challenging. So that's why this cutting plane method is introduced. So to obtain this, one can add cuts. So what do you mean by cut? So suppose you have your feasible region like this. Now you will add you will add your cuts so that it chops off some part of your feasible region what was there before. So this is something that's called as LP. So you can solve this LP. But after that, you'll introduce another constraints, which is called as say Gomory's cut or cutting plane, whatever you call it, in, or by whatever method you find out that cut. So probably that cut, maybe I'll draw it by another line. Color. So this can be your cut. So say cut one. So that chops off some portion of the feasible region. So probably what you have done, you have eliminated some of the points. Probably that this part, if this part does not should not does not contain any integer points. So that means we tried to get to that one side of your convex cell and trying to get it as close as possible. Probably you can add another cut like this, like this, like this. So these are the cuts. So that's kind of extra constraint, and it kinds of making your feasible region shrink and trying to reach to the convex cell. So that's the idea about this cutting plane method. And finally, if you can construct the sides of the convex cell and solve it as LP, and then you will get the solution as of IB. Then let's move on to the branch and bound. So let's talk about it a little bit before I wrap it up for today. So branch and bound. As before, we might have something like this. And probably these are your integer points. What branch and bound does is, suppose this is x1 and this is x2. So this is say 0, 1, 2, 3, 4, 5, right? So suppose you get your x1 to be say 2.5. But it cannot be 2.5. So that means your x1 can be 2 or less than 2 or greater than 3. So what you can do, so first you will branch on these two sides. So this is less than 2 and this is greater than 3. So this is one portion. This is another portion. Now you will solve the LPs in these two subregions again. So in these two blue shaded subregions again, and you will get another set of solutions, right? So there, if one of the variables again is fractional, you will branch again on those two sides and you try to get the solution further. So what happens is that generally it is constructed in the form of tree. So you have a root node. So this is called as the root. Then this is called as left branch and this is called as the right branch. So this can be say xi less than equals j and xi greater than equals say j plus 1 and you solve this. So this could be a node 1 and node 2. Then there could be another branching that you kind of you do. So this could be 3 and 4. This could be xk less than equals to some L, and this could be xk greater than equals L plus 1. Here also you can do some sort of a branching again. And you will proceed. So you'll traverse this tree and until what happens is that all your variables are integer. Then you will stop and that will be your optimal solution. But it might happen that you'll find one integer feasible solution somewhere, but you have to traverse the other part of the tree to get the solution. So I'll talk about in more details in this context. So I think the concept of branch and bound and this other Gomory's cutting plane. So there is a lot to talk about in this topic. But I think in week 5 this class that was not covered mostly, but I'll try to cover it in the next class, or there is another class there, week 6 class or somewhere. So next week the agenda will be first to solve the problems of assignment 5, and then I'll talk about the contents of assignment 6 a little bit, and if there is time I'll go into this details of this branch and bound and cutting plane methods. Okay. Yeah, so and I'll share the Excel sheets and everything that I have, these notes that I have written today. And yeah, so all the best with your assignments. And yeah, if you have doubts, you can post it on discussion forum. So I'll be happy to answer it whenever I get time. But yeah, so just one thing that I found probably few people are discussing something about assignment on WhatsApp groups or something, and you have created inside that course page. So anyone has access to that group. So even props can join, even I can join. So be careful on what platform you are discussing. So yeah, just keep that in mind. And the the idea should be to solve it on your own. But yeah, so just be careful with that. Okay, so with that, I'll stop for today since it's 5 already. So I'll see you all next week. Yeah, thank you.